Imagine organizing a picnic where you want to invite either your family or your friends, but the two groups strongly dislike each other. If both groups show up, the event is ruined. You need one or the other, but never both. This is known in logic as the exclusive OR problem, or XOR. A standard single-layer neural network, often called a perceptron, fails to solve this. A single perceptron can only draw one straight line to separate good scenarios from bad ones. Because the acceptable only family and only friends scenarios sit on opposite sides of the unacceptable both scenario, a single straight line cannot accurately fence off the correct answers. This diagram shows the structural upgrade required to bypass that limitation, a multi-layer perceptron utilizing a 2-2-1 architecture. We have two input nodes, two new hidden nodes, and one output node. Inside each, we apply the neuron equation, multiply inputs by weights, add the bias, and check if the total is greater than 0 to fire a positive signal. Inserting this middle hidden layer provides the exact mathematical space the network needs to process conflicting boundaries simultaneously. Step 1 is defining the operational goal of our new hidden layer. We will program these two middle nodes to act as isolated detectives, each looking for one very specific, mutually exclusive scenario. Look at the top hidden node, Z1. We will assign it a strict logic rule: detect family and not friends. To enforce this rule mathematically, we assign a positive weight of 1.0 to the family input and a negative weight of -1.0 to the friends input. We then set the node's internal threshold, or bias, to -0.5. Let's verify this with the family-only input, where family is 1 and friends is 0. 1 times 1.0 plus 0 minus 0.5 equals 0.5. Since 0.5 is greater than 0, the node fires, outputting a 1. Now we shift our focus downward to the second hidden node, Z2. We give this detective the exact inverse logic rule: friends and not family. To do this, we flip the weights. The family connection receives the -1.0 penalty, and the friends connection gets the positive 1.0 weight. The bias remains at -0.5. Testing this with the friends-only input of 0 and 1 yields the exact same calculation. The math totals 0.5. And the Z2 node fires. These two hidden neurons have successfully isolated our two acceptable outcomes, creating a mathematical firewall that protects against failure. This diagram now reveals the final stage of our network, the output neuron, Y. This node acts as our ultimate decision maker, functioning as a simple OR gate that combines the findings from our two detectives. We need Y to approve the picnic if it receives a signal from either hidden node. So we assign a positive weight of 1.0 to both incoming connections and set the final bias to -0.5. Now we execute the critical test, the both scenario. This introduces the exact conflicting signals that break a single-layer network. We set both inputs to 1 and execute a forward pass. At our first hidden node, Z1, the positive weight of the family input is immediately neutralized by the negative weight of the friends input. Down at Z2, the inverse happens. The negative family weight suppresses the positive friends input, resulting in another -0.5. The second node also outputs a 0. We trace those two zero-value signals into the final Y node. 0 times 1 plus 0 times 1 minus the 0.5 bias equals -0.5. The final decision is 0. Because neither hidden detector found its exact exclusive criteria, the network successfully suppressed the output and prevented the picnic. To verify the entire system, we initiate a rapid confirmation test using an acceptable scenario. Only family is present. Tracing the input to Z1, the positive family weight goes entirely unopposed by the 0 friends input. It easily overcomes the bias and outputs a 1. Simultaneously, the negative family weight hits Z2, ensuring that node is kept fully suppressed at 0. Calculating the final pass at Y, that single positive signal arriving from Z1 is all it takes to clear the final bias. The network outputs a 1, triggering a go decision. By separating the logic constraints into two distinct steps, the isolated positive signals successfully navigated the hidden layer. This chart shows our summary truth table, aggregating all 4 possible input scenarios against their final outputs. The network outputs a 0 when nobody shows up, a 1 for individual groups, and a 0 when both arrive. By calculating these node weights and tracking the inputs manually, you have engineered a verified neural network that solves the XOR limitation. The next step is translating this exact manually verified mathematical node map into automated code using Python and NumPy. NumPy is a programming library designed specifically to handle large numerical arrays and matrix calculations like the ones we just performed. Mastering the mathematics of the hidden layer on paper is the specific, non-negotiable bridge to building complex artificial intelligence systems in code.